Our next speaker is Illyoung Choi of CyVerse at the University of Arizona, and his talk is entitled AI Verde MCP Server, Bridging Generative AI with CyVerse Data Resources.
Hi everyone, I'm Illyoung Choi from CyVerse, University of Arizona. In this presentation, I will introduce a new project, AI Verde MCP Server. This project aims to integrate generative AI capabilities with CyVerse data resources, providing direct access to data storage that is essential for research and education. Generative AI is currently having a profound impact on research and education. Generative AI is accelerating research by enabling quick information search, literature review, hypothesis generation, and data interpretation. Generative AI is also improving teaching and learning by supporting instructors with course material creation and assignment drafting, and providing students with personalized Q&A, content simplification, and interactive learning experiences. However, when researchers and instructors adopt commercial generative AI for their work, they often encounter several limitations. First, there are significant challenges in budget and group management when trying to use these tools across courses or for research teams. This is because commercial solutions often lack the group payment and per user budget controls that institutions and large teams require. Second, there's often limited access to diverse AI models. You are usually restricted to the models that the provider offers, which might not always be the best fit for your specific task. Third, you will find limited customization for specific research domains or when working with private data. Commercial solutions often can't effectively understand or integrate your unique research context unless you feed them a significant, often impractical amount of your specific research materials. And finally, a major concern for many, especially in academia, are the data privacy and security risks. Using sensitive research data or student information with third-party commercial platforms raises significant concerns about where that data goes and how it's protected. AI Verde is an integrated generative AI platform designed to address the issues for research and education. Our platform is built specifically to empower researchers and educators in several ways. First, AI Verde empowers research teams to use AI directly on their private data. This is crucial for sensitive or proprietary data sets that can't be exposed to general commercial platforms. Second, for our academic users, it assists students and educators with AI using customizable course materials. This means you can integrate AI capabilities directly into your learning environment, tailored to your curriculum. We also tackle the administrative hurdles head-on by providing integrated group payments and budget management. Individual subscriptions are not required for students or research team members. Furthermore, AI Verde integrates a wide range of large language models, including both commercial options and powerful open source models. This gives you the flexibility to choose the best tool for your specific task without being locked into one provider. For example, some models excel at coding, while others are specialized for tasks like literature review. To ensure broad usability, the platform offers flexible access from diverse clients or directly in your code. And finally, to ensure robust performance for these demanding AI workloads, AI Verde leverages a dedicated hardware from CyVerse and Jetstream 2, a national NSF-funded infrastructure in the United States. The AI Verde web interface provides a familiar chatbot interface for direct interaction with generative AI. Beyond the chatbot, CyVerse is developing features to manage research team and course environments. These will include the ability to configure team and course general settings, manage members and roles within the team or course, allow instructors to control budgets for an entire team or course, or set per member budgets, enable users to select AI models and manage API keys for access, and finally, allow researchers and instructors to upload files to establish external knowledge. In general, there are two primary ways to customize large language models with external knowledge bases. The first method involves uploading files and indexing their content for retrieval augmented generation, or RAG. AI Verde will first search for related content from the uploaded files using the index. This content is then passed to LLMs as a context. However, this method of customizing LLMs does come with some limitations, particularly for research and data-intensive tasks. First, uploading large research datasets for indexing is not practical or even feasible. This is because RAG is optimized for document-level content rather than massive raw data files. Second, for data management, you cannot ask LLMs directly to perform file system operations like moving files to another directory, deleting them, or renaming them. LLMs don't have direct access to your file system or capability to execute any commands. The second method is using the Model Context Protocol, or MCP. With the MCP, AI agents can access external data services directly. This is a fundamental difference from RAG, as it moves beyond just searching indexed files. Users can gain extended assistance with identifying and utilizing documents within external data services, such as IRAs. Information obtained using the MCP can also be passed to LLMs as a context, effectively providing them with a dynamic knowledge base. Now let's delve a bit deeper into the Model Context Protocol. The Model Context Protocol consists of three main parts: the MCP host, the MCP protocol, and the MCP server. The MCP host is essentially the client application or environment that runs the AI agents, where users interact with the system. For instance, VS Code, Cloud Desktop, AI Verde web interface, or even your own custom code can serve as an MCP host. Users directly interact with the MCP host to initiate their AI tasks. The MCP host then communicates with the MCP servers using the MCP protocol. With this protocol, the MCP host learns the available APIs and how to make requests. This allows client applications to dynamically adapt to the services offered by different MCP servers. Lastly, MCP servers then provide various APIs for accessing data or performing specific actions. For example, a Google search MCP server allows users to search the web using Google. And Importantly for our work, the data store MCP server provides access to research data sets stored in the CyVerse data store, which is built on top of iOS. CyVerse is currently developing two distinct AI Verde MCP servers. The first is the data store MCP server. This server provides general file system access to the CyVerse data store, which is built on top of iOS and storing data totaling 7.2 petabytes. It also provides access to the CyVerse data commons, which stores metadata for 279 public datasets totaling 76 terabytes. The second is the RAG MCP server. This server provides access to the indexing system of AI Verde for user-uploaded documents. We will use this to simplify the existing RAG process for customized response generation. Let's go a little deeper into the data store MCP server. Imagine a user asking an MCP host for a data set stored in the CyVerse data store. The request is passed to the data store MCP server using JSON RPC over HTTP. Now the data store MCP server routes requests based on their purpose. If the server receives data access request to the data store, such as for actual file operations like reading, listing files, it leverages the Go iOS client to communicate directly with the CyVerse data store where the data resides. However, if the server receives a request to search a dataset from the community public dataset catalog, it utilizes the CyVerse Terrain API to communicate with the CyVerse data commons. The CyVerse data commons serves as the centralized catalog for these community public datasets and their associated metadata. Now let's walk through a usage scenario to understand how the data store MCP server works. Imagine a user requesting a dataset in the data store. The user begins by making the request in natural language to the MCP host. The MCP host then translates this natural language request into a JSON RPC request using large language models. This JSON RPC request is then passed to the data store MCP server for processing. The data store MCP server proceeds to find the requested dataset from the CyVerse data commons and returns the output as a JSON RPC response. Finally, the MCP host interprets this JSON RPC response using large language models and generate a natural language output text for the user. The data store MCP server currently implements APIs for listing, searching, and reading files on the data store, as well as for searching and retrieving metadata from the data commons. Now let's see this in action. Here's a quick demo showing how the data store MCP server works. For this demonstration, I used VS Code Copilot as the MCP host. You will see how I asked Copilot to show me files and directories of the TerraF dataset with its exact path in the data store, along with their access permissions. Copilot was able to find the directory listing API correctly, automatically. And as you can see from the video, Copilot was able to successfully retrieve all the requested information from the data store. Let's move to a second demo showcasing more complicated jobs. For this scenario, I asked Copilot to find the read drought stress dataset without specifying the exact path, and also to provide detailed file information. This time, Copilot selected the metadata search API that searches datasets from the data commons. Yeah, Copilot successfully located the dataset in the data store, and then it tries to retrieve the information from the data store. This demonstrates its ability to interpret complex requests and interact with both data commons and data store. Following that, I then asked Copilot to summarize the README file within the dataset. And again, Copilot was able to seamlessly read the file content and provide a summary using the large language models. This seamless interaction highlights the power of the MCP server in bridging generative AI with the external knowledge bases such as the data store. So what's next for AI Verde? The data store MCP server is currently in active development, and we have several key enhancements planned. First, we plan to add more APIs for comprehensive file system operations within IRAs, alongside implementing OAuth authentication for private data access. We also intend to add caching for faster response times. Looking at broader AI Verde platform, the development team plans to enable instructors and users to add MCP servers to their own teams or courses, empowering them with greater autonomy in teaching and research activities. To conclude, AI Verde is an integrated generative AI platform specifically designed to empower research and education. It is built to address unique needs of academic users, supporting private data and customization. The data store MCP server will become a key component of AI Verde. This server provides direct access to both the data store and data commons, which archives 76 terabytes of community public datasets. MCP hosts automatically handle input and output for the MCP server APIs, significantly simplifying access to these data resources. And finally, we also plan to open source the IRO's portion of the data store MCP server code in the future, thereby contributing to the IRO's community. Thank you for listening, and I will be happy to answer any questions you might have.
All right, thank you. Do we have any questions?
Hey, Illyoung, this is Terrell. Do you have a couple of examples that you can share of people that have already started playing with this that were surprising or more interesting than others? Or is it just so new that nobody's poked at it yet?
Oh, not yet. Yeah, it's relatively new. Actually, I just started releasing this. Releasing this project to other groups of the forest research team, who captures images with the using drone. Forest images using drone, and they want to use AI Verde and MCP server for processing their drone image data. So we are going to have some usage scenario with them next week, probably. So it's a brand new one.
Okay, got a question back here.
Okay, there are three questions here. How will AI Verde integrate with iRods, and what will the relationship look like? Could you provide some more concrete examples?
Yeah, the example
I'll
is,
just fill them all. Yeah, sorry. I'll go ahead and ask all three then. Which human language is supported in AI Verde? Only English. And since AI Verde is part of the CyVerse ecosystem, does this mean it is designed to work specifically with discipline-dependent data, or can it handle data from any discipline stored and managed within CyVerse?
yeah, currently we wanna integrate IRAs. I mean, the data store actually runs IRAs inside. So we wanna integrate IRAs and data store using the MCP server I presented. Currently, it only provides a read-only access for, just reading and summarizing, searching data sets. But we want to provide the right access as well, for managing the data set as well using AI Verde. So that will be done using the MCP server that I presented today. And then about the second question, we currently support English, but it's okay to use any other languages because the languages are mainly handled by the large language models, not by this other part of the system. So yeah, as long as the large language model supports other human languages, yeah, we can support those languages as well, like Hindi or Korean or Spanish. We already tested the Spanish, but yeah, we can support any languages as long as large language model supports. And for the third question, yeah, we don't care about the discipline. We currently tested the AI Verde with CyVerse internal technical documents and the bioinformatics data and TechLunch Arizona, the startup related documents as well, and the ECE course materials and HPC documents. We actually tested it with a lot of different types of classes and lab documents. So yeah, I think we don't actually care we can support any type of disciplines.
Okay, my question is, this is Corey. My question is, so you've implemented this MCP design pattern. Does this lead to the results being far more accurate, or does the AI still have a tendency to report incorrect information?
Yeah, that's a really good question. The reason I used Copilot was the Copilot has the large language model that can better control the MCP systems. Some other language model, large language models like Llama, recent version of Llama does not support the MCP well. When I use the same questions I used in the demo, it doesn't use the same APIs. When I tried different LLM models, every time I use different models, it runs differently. So that's the one challenge I currently have. I need to find which model runs the best. Currently, the Copilot and Cloud Desktop ran the best with the MCP system. Yeah, based on the LLM models, it runs differently. And then sometimes it returned inaccurate result as well. I mean, when I search for with data, sometimes it just returns random output. I mean, it found the random data set and then returned the wrong output. Sometimes it generates hallucination as well. Like for non-existing files in the iRoads directory, it returned hallucination. Like, I mean, it returned non-existing replicas. I mean, it generated random hash code as well. So that's the challenge I am currently having.
Okay. Any final questions for Illyoung? All right. Thank you, Illyoung.
Thank you.